Good day. Our next video for Tuesday, January 31st is about real world applications of trig functions. Real world applications. Now, the key to this is we're going to approach these in really three different ways. The first way is you're going to be given the equation of a situation already. All right? And when you're given the equation, then you're going to want to answer questions about that equation or that situation. And in general, the goal here is it's really exploring the parts of a graph, like, how's the amplitude help us? Well, it'll help us find minimum and maximums, right? It'll tell us how far apart they are and where they're at. What about the period? The period will tell us for how long things last, right? So one period could be like one revolution of a Ferris wheel or something like that. So we'll be looking at these kinds of things. And then up, down, and left-right phase shifts are involved as well. The up-downs could affect the maximum and minimum. The left-right could affect, sort of times of where things will occur. So we're going to look at least one question of each type, and then you have your reading, which will have at least a question or two of each type as well. So I'm grabbing some different questions than are what in your reading, just so you experience seeing different things, okay? And our goal then with equations will be to answer questions about that function, that equation, or about the graph. And we'll be pulling information that we know. So we'll give you some examples of that. The next situation is we're going to be writing the equation or writing the function. They're going to give us situations and information, and we're going to use that to write an equation, or at least an approximate equation. And then in the same vein, part two of this, that's sort of part one, where the information they give is fairly obvious. The maximum height is, the minimum height is. Okay, I can use those to get the amplitude. A part two of this is where you'll have to write the equation. They give you a data table. And so we're going to use a data table to then write a trig equation. And I'll show you a graphics calculator way to do it as well. I'll probably do that in class. But this is what we're doing today. It's quite involved. However, it's very similar to what we had to do for graphing and to find out information. So let's get started on this and we'll move forward. So here is the first type of problem that we're going to do. This is one where an equation is given, and I'm going to circle that right here. Okay, and we'll just read it to you at this point. Since some of you probably have a hard time with my handwriting, so, and cursive, which sometimes I write in when I'm writing on these things. So I'll just read through it so you have an idea what we're doing. The distance of a certain satellite is north or south of the equator, and that it is given by this equation: y equals 3,000 cosine pi over 60t plus pi over 5, where t is the number of minutes since liftoff. A, we want a graph for 0 less than or equal to t less than or equal to 120. I'll tell you why we're going to go ahead and do that. This is not something you're going to do in your assignment, but you may want to just automatically add it as a part of the questions that you're going to do. Just kind of graph the thing. It'll help you sort of understand and work out what you're trying to find every time. And I'll show you how to do that. The second question is, what is the farthest distance that the satellite ever reaches north of the equator? Okay. And then the third question is, how long will it take to complete one orbit? All right. So there we go. Let's kind of work this out and we'll go from there. So to graph this, I want to get the information. So the amplitude is 3,000. Okay. We're moving up and down. So that'll affect the amplitude. But notice we need to factor to do that. So we'll factor out pi over 60 t. And what times pi over 60 gives pi over 5? It'll be 1/12. All right. And so that means we're going to move up and down. We go 0 up and down because there's nothing outside of the parentheses there. But we go left and right. We're going to go to the left 1/12. All right. And then our period is 2 pi divided by pi over 60, which is equal to 120. And now you know why they want us to graph this from 0 to 120. Because that's one period, all right? So that's a good thing. So let's kind of map this out on a sheet of graph paper here, okay? So if I was going to draw my graph, I would look like this. Let me make this 120. And I noticed I made a mistake. Not 1/12 here. I need it to be up here. I need it to be 12. Because 12 times pi over 60 is pi over 5. Okay? That basically means we move left 12 minutes. So let me erase this as well. Now I can fix this. Okay. So what we're going to do is we're going to go 12 minutes to the left because we moved 12 minutes to the left. And then we're going to add 120 to that, which is 108. Okay? And that gives us one period of 120 minutes. Okay? So, when you have these graphs with real data, it makes for bigger numbers and a little more challenging to set it up. So now we want to go halfway between those, all right? Which would be halfway between, those look to be about the same size. That's at about 48. So 108 plus negative 12 is 96 divided by 2. And then 48 plus negative 12 is 36 divided by 2. So about 18. And then we'll add 48 plus 108 is 156 divided by 2 is 78. all right? And as you can see, each of these spaces here is 30 minutes long all the way, all right? So now we can go back to the graph, okay? We've moved it left. We have our period mapped out, 120 minutes. And now we need our amplitude. So we're not moving up or down. So the amplitude, this is just 3,000. And this down here is negative 3,000. Okay? And then all we need to do is plot our cosine curve. All right? And if you remember, cosine starts here, and then it has a 0, then it has a minimum, then it has a 0, then it has a maximum. And so there is our cosine curve. Okay? Everything equally spaced the way it's supposed to be. So that's the graph. So now let's go to question B. Okay? Question B says, what is the farthest distance that the satellite ever reaches north of the equator? What is the farthest distance that the satellite reaches north of the equator? And so, furthest distance would be given by the amplitude, right? And north of the equator would be positives, south of the equator, negatives at this point. So the furthest distance, one of the ways we could see it is illustrated on the graph. It could be that value, all right? And so the maximums are where the furthest distance is. Now, if we had moved this up, let's say, or down, then that maximum would change if it had been moved up or down, all right? But we're looking for the furthest distance or the maximum distance that the satellite ever reaches north of the equator. And that distance, of course, is going to be the amplitude. So we would answer that as 3,000, I believe, miles here. Is it miles? I don't think they told us what y was. They told us that t was the number of minutes. So I believe it would be 3,000. Let me check this really quick. I'm not sure if they gave us whether it was miles or not. That's interesting. Yeah, I just didn't catch that in the problem, so I keep looking for it. Yeah, it was miles, okay? Probably because we measure the distance around the Earth in miles, so that would make sense. Now, how long will it take to complete one orbit? So one orbit in this case is where the satellite goes from where it starts and then comes back around to the same spot. So this would be one period. So how long does it take? It would take 120 minutes. And we know it's minutes because t was in minutes. All right? Now, another question you could ask would be a little bit different. So I'm going to make a question D. Okay, question D, just for fun. So question D would be, what is the distance and location from the equator equator after 30 minutes. Okay? So 30 minutes, we would go to the start, which was negative 12, add 30 to that, which would get us to 18. Oh, I don't want to do 30. I want to do like 36. And add that to negative 12, and we would end up here at x equals 24. All right? So 30 minutes would be this number here on the y-axis. But how do we get that number? Well, that means we would plug 24 in for the time. So we would then say y equals 3,000 cosine pi over 60 times 24 plus pi over 5. Now notice we don't just plug 30 in there, 36 in there. It's 36 minutes after 36 minutes. So you start on your graph at negative 12 minutes. So that's why you put in the 24. And so this just becomes a calculation. All right? And for fun, we can calculate that on Desmos. All right? So Desmos, and let's go to, do we want the graphing calculator? Let's see, let's grab the scientific calculator, and we'd enter 3,000 cosine of pi over 60, pi divided by 60, and then and we would multiply that by 24. Let me put a times 24 there. And then we would add the pi divided by 5. And there would be our solution. Right here, we would be at 2,998 miles. So very close to the maximum, but not quite the maximum. All right? And so 2,998.37 miles. So now that we have found the distance and location after 30 minutes on our calculator, that gave us a number. It was that positive or negative? Now I can't remember. Sorry, I had to step away for a second. So we'll have a little fun here, and I'll type it in my calculator again instead of bringing it up on the screen. For you, it's just a quick scroll back. For me, it's slightly more effort than that. Okay. Okay, so I did that on Desmos, and I got 2,998.4, and I just did it on my calculator, and I got a negative 927.1. So the question is, which one's right? Or do you remember something that you have to remember? The one that's correct is actually this one, because Desmos was in degree mode and this one's in radian mode. And if you look at this problem, it needs to be in radian mode. So there was a perfect example of why you always need to check your mode before you do a problem on a calculator. And so now I can answer this question. What's the distance in location from the equator? Well, it's 927.1 miles from the equator. All right. And it's south because it's a negative number. And that matches with what we see on the graph. Do you see that? That we're a negative number and we're, so therefore that would mean that we're south of the equator, okay? And so that gives me a much better idea of what's going on, okay? Now, just so you know what's actually happening with this satellite, well, if you think of the Earth, here's the equator. What's going on is a satellite is traveling around the Earth like that. So it's above the equator and below the equator. So it's traveling in an ellipse, circle sort of pattern around the Earth. And that's why you can say it's 3,000 miles above or 927 miles above, et cetera, et cetera. All right? So that's one question. So here's another question that we could ask, continuing this problem. Question E, at what time will the satellite be 1,000 miles above the equator? Okay, now notice that's a positive number, and so we can just once again plug it in, except the 1,000 is the y, so we get 1,000 equals 3,000 cosine pi over 60t plus pi over 5. So divide by 3,000 on both sides. So we're just going to solve the equation now. A little more complicated equation, but not too tough. So we get 1/3 equals cosine of pi over 60t plus pi over 5. And so we have to take the inverse cosine of both sides. So the inverse cosine of 1/3, all right, is equal now to pi over 60t plus pi over 5. Then we subtract pi over 5, so the inverse cosine of 1/3 minus pi over 5. And then we'll divide by pi over 60. And that will equal t. And then we calculate that out on a calculator. All right? And so I'll just do that right here. We'll do the Desmos calculator again. And let me shrink this down just a bit so we can see what we're entering. And we're going to go ahead and do inverse cosine. Now, this time I'm going to switch it to radians, okay? So I go to function, I do inverse cosine of 1/3. So I'll go back to the main menu, 1 divided by 3, parenthesis, and then I subtract, oops, let's go back and press, let me see how I do this. Let's go back out here and we go delete, delete, and then we click out there, and now we hit the parenthesis, and then we subtract another fraction, pi divided by 5. Now, that's the numerator, okay? And then, and this is what I'll do sometimes to shorten it. There's the numerator. Notice I don't round this off at all. Now I'm going to divide, delete, and go out here, and then we'll go to the next one. And so I'll take my answer, and I'm going to divide that by pi divided by 60. Okay? And there's my answer. So that's now 11.5. In this case, it's time, 11.5 minutes. All right, so I've done everything in radians. So I get 11.5 equals t. Now, if we go back and we look at the graph that we had, if you'll remember, we want to know where this is equal to 1,000. And so 11.5 is right here. And so boom, that's going to equal 1,000 right there. So we know it's 1,000 miles above. Now, if we wanted, because it's radians, we could subtract the 11.5 from 108, and that will give us the same y value of 1,000 as well. So it actually occurs in two places. So using your graph to kind of see what's happening. So 11.5, 11.5 is correct. But if you'll notice, it's not 11.5 we subtract from 108. We got another 12 minutes, so it's 23.5. So if you do 108 minus 23.5, you'll be at 84.5. All right, I believe that would be correct. Yeah, and this is 78. So yeah, that's about right. So just looking at the graph. So this is a case where you get a second answer, 84.5 minutes, as well as 11.5 minutes. Okay, and there would be your two answers. Now notice how I use the graph to kind of help me understand the problem and so forth. And that's a good idea when you're working on problems like this, okay? So there's everything, 5 questions, nice, right? Quick review, let's go back. We had a formula, they asked us to graph, they asked what the furthest distance was, that was amplitude. They asked how long it would take to complete one orbit, that was 120 minutes. And then I added 2 questions. What is the distance and location from the equator after 36 minutes? Okay. And then also, at what time will the satellite be 1,000 miles above the equator? All right, and that was our last answer. Okay, so hopefully that helps. That's a beautifully done problem where you're given a formula. So for this one, our primary question, question 1 is we want to find a sinusoidal function of this form that will fit this data table. And in case you didn't know it, temperatures in any city, and if you want to do it to find out like the average monthly temperature for your city in Texas, be it El Paso, Amarillo, or Tyler, Texas, anywhere in Texas, Galveston, You could look that up online, find the average monthly temperature, and you could do that and find the equation. So this is really the first question we have to answer, is be able to write the equation from the set of data. And so in order to do that, in order to write an equation, we need to find first the amplitude. Okay, amplitude's an easy one to find, and we'd like to find it. So how would you do that for this? All you have is a data table. How would you find out where the peaks and valleys are? Okay, so what we would do is we would take the highest y value and the lowest y value and subtract them. 56 minus 24.2. And then remember, that's twice as big because you got a midline in between, so you got to divide it by 2. So you take the highest value and the lowest value, and that would be your amplitude. So let's figure that out. So 56 minus 24 is 32. So this is 31.8 divided by 2, which is equal to 15.9. So, and in this case, it's 15.9 degrees, has a label. So that's our amplitude. That's our value for A. Okay? And I'll make these colors so that the work matches. All right? Let's go, what would be the next thing that we would find? Well, the next thing we could find would be how far up or down were we moving? How far up or down? And so, as you can see, with 56 and 24, we are not centered on 0 for the midline. So where would the midline be? So essentially what you want to find here is the midline, all right? And that'll tell you how far you moved up from 0. Well, how do we find the midline? Well, we're going to use the same two numbers, 56 and 24.2. And all we want to do is find halfway between these two numbers. So if you do that, you end up with 15.9 again. But what do you do with the 15.9? You just add it to the 24.2, 15.9 plus the lower value will give you 0.1, 10, 40.1, and 40.1 is halfway between 56 and 24.2. So this is how far you had to move up from 0. So now we found our B value, okay? So the next thing to find would be our period, omega here, which is typically the variable they use for period, by the way, or the value we get from finding the period, okay? So what we know is that if we're looking for a period, okay, then 2 pi over omega is equal to the period, okay? And all we know up to this point is what our maximum and what our minimum is. So what we need to do is we need to think about a graph of this. What does a graph of a sine function look like? So let's draw it, okay? The graph of a sine function looks something like this, right? And this is one period on the x-axis, one period, okay? Now, if you think about it, here's the maximum, and here's the minimum. And so what's the distance between the maximum and minimum? You're right. That is half the period, because remember, if we know the period, we cut it in half, and then we cut those in half to get the maximum and mins. So this is half of the whole period. So the distance between 56 and 24.2, so we take 56 minus 24.2, which we found before is 31.8. That is the period, okay? This is the period. Or, excuse me, half the period, okay? So we need to double that. So we take 2 times that. Notice all we're doing is really subtracting, multiplying, and dividing using the data that we can see. So 2 times that is 63.6. And that is the period, okay? Now that I have the period, I want to find omega, which is the number I plug into my function. So that's where this becomes a little bit different and something you want to really pay attention to. So then we take 2 pi over omega, and that's equal to 63.6, okay? So we cross multiply, so 2 pi equals 63.6 omega. And then we divide by 63.6. So 2 pi divided by 63.6 is equal to omega. And if you wish, you could calculate that out on a calculator to approximate it. So 2 pi divided by 63.6 in this case is equal to 0.09879, okay? And that's the omega value that we plug in, okay? So finally, we have one more thing to do. Is this function moved left or right? All right, so I'm going to ask that question. I want you to think about it for a sec. You can pause the video while you think. So the final thing we have to do is the left-right shift. We have to figure out how to find phi, Greek letter phi here, which usually represents that. How do we find the left-right shift? Well, with the left-right shift, all you want to do is pick one of the data sets. Now, generally, we do this by month, not by day. So 1 goes with 24.2, 5 with 47, etc., all the way down, okay? All you need to do is pick one of those dates, okay? And so say we pick April, all right? So April is 4 and the temperature is 39.7. So we fill in all the other information that we have. So let me circle all these pieces of information and we put them in the function. So what we have for our function is y equals a 15.9 sine of omega, which is 0.09879 x minus phi, all right, and then plus b, which in our case is plus 40.1, all right? And then we plug in our value for x and y and calculate phi. So our y value, so we're going to use this row for April, and you can use any one. So there are going to be slight variations for what phi could be, all right? So my guess is they'll probably have a range to grade, or they'll tell you which piece of data to use. So the y value is 39.7. And then we have 15.9 sine of, and instead of using the decimal here, I don't want to have round off error when I solve this. So I'm going to put the 2 pi over 63.6, which was this alternate answer, which is not a rounded off answer, okay? And that's important for calculations. Our x value times x will be the 4th month, April, minus phi, Greek letter phi, and then plus 40.1. Okay, so now we have to solve this for phi. Phi is the mystery variable we have to solve for. Okay, and so I'm going to do that. I give myself a little room, and I'll proceed forward. So the first thing I'll do is subtract 40.1 from both sides, and I get negative 0.4 equals 15.9 sine of 2 pi over 63.6 times 4 minus phi, and I subtracted 40.1 from both sides to get that, okay? Then the next thing I'm going to do is I'm going to divide both sides by the 15.9, okay? Now, unless this is a nice number, so let me see, negative 0.4 divided by 15.9. That is not a nice number, so I'm going to leave it like that. You do not want to do your calculations and have round off error, because then your problem will be wrong. So we're going to leave it as negative 0.4 over 15.9 equals then the sine of 2 pi over 63.6 minus phi. All right, so now we have to take the inverse sine. So the inverse sine of negative 0.4 over 15.9, all right, equals 2 pi over 63.6 times 4, forgot my times 4 up here, minus phi. And now all I have to do is subtract the 2 pi over 63.6 times 4, which will, when I subtract that, I get the inverse sine of negative 0.4 over 15.9 minus 8 pi over 63.6, and that's equal to negative phi. So if I divide by negative 1, that'll change the signs. And so this is the answer for phi. And that's what I put in the calculator. Okay? Now, I would make sure I'm in radian mode, all right, for this, which I am on my calculator. I've showed you this on Desmos before, so you know how the Desmos calculator works. So just work through this, okay? So I'm doing it on the graphing calculator now. And if everything works out, I end up with 0.4203. Okay? And that's my approximation. Okay? So what's that mean? That tells me what the, this is the phase shift, right? Well, it's not really the phase shift, it's the amount for phi. The actual phase shift is you would have to divide it by the 2 pi over 63.6. But this would be the value that I need to go into this function right here. So it's the last value. So now I can write the whole function, which would be, and here's your final answer, y equals 15.9 sine of 2 pi over 63.6 x minus phi 0.4203, because we don't want to enter this whole thing there. And then plus 40.1. And that was what we were asked to find. What is the equation of this function that fits this data table? Now, in class, I'm going to show you another way to do this called a regression equation. And you may have learned about it in Algebra 1 or Algebra 2. But I'll show you how to do it on a graphing calculator. It will actually should give us an equation very close to this. So now, once you've done all this and you've developed your equation from the data table, and again, I'll show you another shortcut tomorrow for this, but now you can ask the same two kind of questions. Remember, this modeled monthly temperature, so you could say, what would be what's the monthly temperature prediction for the 9th month, all right? And so then you would plug in 9 for x, and you would evaluate what this would be. You could also say, when will the temperature be 50 degrees Fahrenheit? And so what you would do in that case is you would plug that in for y and then solve for the x. So very much like what we did on the last one, when you solve for y, be sure not to divide or multiply anything. Simplify it all the way down and enter that big expression in your calculator. When you plug in the 9, you can just type it in the way it appears with the multiplication times 9 here, and then you're good. So times 9 right here, and everything should work out pretty simply. All right, and then hopefully the prediction for what's the temperature in the 9th month would be fairly close to the 49.4. And in what month will it be 50 degrees? Hopefully that will also come out to be fairly close to the 8th or 9th month. All right, maybe you'll get like 8.5, or, which would be 2 weeks into the 8th month or something like that. So anyway, that would be how you would do this problem. Okay. Other than that, that's a pretty squared away approach to this type of problem that you'll see and the type of data you'll see.